Alright, so we did optimization problems for multivariable functions, find the critical values, test to see if they're max and mins. Today we're going to do applications. Alright, next step is to apply that. And so applications of optimization. Alright, so we have a company that produces X units of product A, Y units of product B. So A and B are some type of product that they manufacture. There's my cost equation for producing both of those items. We want to know how many units of each product should they produce daily in order to minimize the cost. What is the minimum cost, and verify that you found. Just like we did with one variable functions. Same idea. Alright, so first thing we have to do is find my critical values. Alright, which means find my first order derivatives and set them equal to 0. Alright, so my first order derivative with respect to x and with respect to y. Alright, so with respect to x first, those are the only two x values, so derivative with respect to x is 2x minus 50. Set it equal to 0, that's a key step. And then my first derivative with respect to y, again, these are the only y values. So 8y minus 32, set it equal to 0. And so this is the simple case where it's just simply solve for x, solve for y in each individual equation. So we'll do that. So this one I'm going to solve for x, so I get 2x equals 50. My x value is 25. And my y value is 4. Alright, so there's my critical value. 25, 4 is the critical. Alright, and so my guess is that's the answer. I will have to verify. I'll do my verification up above, but I'm going to go ahead and plug in my numbers. I'm guessing they want to make 25 units of A and only 4 units of B, and I'll find my minimum cost in a little bit after I verify. Alright, so to check that this is actually giving me the minimum that I'm looking for, not a saddle point or a maximum, I test using my D formula. Remember, the D formula is second derivative with respect to x times the second derivative with respect to y minus my mixed derivative squared. And so I'm just going to, as I'm finding my second derivatives, I'm just going to go ahead and plug them in my formula. Alright, so I'm looking here first, taking its second derivative with respect to x. So the second derivative of that with respect to x is 2. Then I'm going to look here, take its second derivative with respect to y. Well, the second derivative with respect to y is the only y term, so that's 8. And then the mixed derivative is 0. You can find either one, but it zeroes out, right? If I take the second derivative here with respect to y, well, there's no y value, it zeroes out, right? And whenever it's a simple case like this, these are always going to come out just numbers, single numerical values. And so my D formula says, well, 2 times 8 is positive 16, so that's the yes. It's not a saddle point, right? It means it's a max or min. So yes, it's an extrema. And then I make sure it's the one I'm looking for. So I take my second derivative with respect to x, which was 2. That's positive, which means concave up. So yeah, it's the minimum that we're looking for. So it checks. Alright, so it does find me the minimum cost. Well, now I find the minimum cost by taking my 25 and my 4 and plugging it back into, remember, all the way up top, back into this original expression. So this is the function that I'm going to plug my critical value into. So for the x, I'm going to plug 25 in. For the y, I'm going to plug 4 in. And just make sure you're careful. It's really easy to accidentally mistype one of those or miss a negative or something. It's something I would do. So always check my answer. Make sure I typed it in correctly as well. Alright, so again, that critical value is going up there into my original function. 25 for x, 4 for y. And when I do that, I get that my cost is 1,311. Alright, and so there's my first example. Alright, my next example, which for some reason is labeled 3. Alright, so we've got so this is actually the one we set up way back at the beginning, in the start of these notes. Alright, we've got a concert. They produce two t-shirts. A cheaper version, which is $18, and a more expensive version, which was $25. And so the revenue generated from the sale of each of those in thousands of dollars and thousands of t-shirts is given by that revenue equation. The cost is given by this equation. Again, keeping in mind everything's in terms of thousands. All right, the first step is to find the profit equation. So profit, remember, is the revenue minus cost, even in these more complicated functions. Alright, and the biggest thing is just make sure you're careful with your subtracting and collecting like terms. It's really easy to miss a negative or miss a function value. And we actually found this one earlier, but I am going to go through it again, just good practice to remind you what it was. But we did find this in the first set of notes. Alright, hopefully I distributed my negative right. Everything in here should have an opposite sign. It does. And then remember, I can only add like terms together, meaning they have to have the same variable parts. The only ones that have the same variable parts are my x terms and my y terms. Alright, so this simplifies to negative 4x squared, negative 3y squared plus 6x times y minus 2x. 6y when I add my like terms, and then add 12 at the end. Alright, and so there's the profit equation that I want to optimize. Alright, so I'm going to make sure I'm careful. So method of calculus means find your critical values, which means find your first order derivative, set them equal to 0, and solve. Alright, so first derivative with respect to x, first derivative with respect to y. So first derivative with respect to x, negative 8x, zeros away, 6y, minus 2, zeros away, zeros away. Alright, so there's my first derivative with respect to x, and I'm going to go ahead and set it equal to 0. Because like I said, that's a key step. You want to make sure you always show that. Alright, now my first derivative with respect to y, zeros out, negative 6y. Plus 6x, zeros out, plus 6, the 12 zeros away. Again, set it equal to 0. And so this is a linear case, which means I can solve this. You can solve by substitution, and if you want to use substitution, you're always free to do that. I'm going to use my matrix, so this is the linear case, which means I can set both my equations in the standard form, which I have to do first before I plug them in my matrix. Alright, x value first, y value second, and the constant moved to the other side. So both of these I will have to do some moving over. I have to move my constant over. And so the first equation is negative 8x, 6y. When I move the 2 over, it becomes a positive 2. And that one I have to move my 6 over and reorder it. Positive 6x first, negative 6y equals the constant negative 6. Plug it into your matrix. It's 2 by 3. And just make sure you're careful when you're typing it in. And show this. This is sort of the work. Alright, so we do the RREF. Remember I showed you how to do that when we were practicing these. Alright, you go to your calculator, you type in your matrix, then you do the math. You scroll down all the way and you want the double RREF, our matrix that we plugged in. And then it should simplify to that. Alright, and so then our answers are, remember the first value is the x value, the second value is the y value. So there's my critical point. So the critical is the point x2, y3. Alright, and so this was the x value. So remember it's in thousands. So we want 2,000 of the 18 and 3. And again, I'm going to write it either way. So one way, you can either do it with words. Write out the word 1,000. Or you can multiply by 1,000 and write out the number 1,000. Either way is fine, right? But 1,000 should be included, right? Selling 2 t-shirts is a lot different than selling 2,000 t-shirts, right? Selling 3 t-shirts is a lot different than selling 3,000. All right, what's the maximum profit? Well, I go and I take my 2 and my 3 and I plug it back into my original expression. So I go all the way back up here and plug my critical value into this expression that I found. So again, I'm going to plug in my 2 and my 3 into this function. And just make sure you're very careful when you plug your 2 in for x and your 3 in for y into that original expression. And so again, just make sure you're very careful when you're typing it out. Alright, so when I do that, I get this is 19, and remember it's 19,000, or again, you can write the decimal, $19,000 in profit. Right, that's the maximum profit. My guess right now, and then the last step is to verify. Alright, so the D formula, I'm going to write it down. It's the second derivative of profit with respect to x times the second derivative with respect to y times one of my mixed derivatives. Don't forget it's my mixed derivative squared. Alright, so I got to go back and find my derivatives. I'm going to go up here because this is where my original function was. My original derivatives are. And I'm going to find them, and then I'll plug them in. Alright, so I'm going to erase this to give myself a little more space to write out what my derivatives are. Alright, so my second derivative with respect to x, my mixed derivative, and my second derivative with respect to y. So this is where I'm going to put them. And they should just come out numbers. Whenever it's the linear case, they're just single numerical values. And so I'm going to look here first, take its derivative with respect to x. Well, that comes out -8. And I'm going to still look here, take its derivative with respect to y. Though that's a +6. And now I'm going to look here, take its derivative with respect to y, which is -6. Alright, so those are my values. I'm going to go plug in my D formula. So -8 for the second derivative with respect to x, -6 for the second derivative with respect to y, and a +6 for my mixed derivative. Alright, so plugging those in, -8 there, -6 there, +6 squared. Don't forget that's a +6 squared. Alright, when that multiplies out, that comes out to +12, so yes. Alright, that checks, yes. It's an extrema, meaning it's not a saddle point, and then I check my second derivative with respect to x, which is -8, right? And it's the one I want. It's turning the right way, right? That's concave down, which means it's turning down in both directions, and so yes, it checks. It is my optimum value. Alright, so the check is yes, it's the turning point. Yes, it's turning the direction I'm looking for. So that's what we're looking for in our explanation, to show and interpret, right? Check that it's an extrema, and then check that it's the right extrema. Alright, the next example. We're making 2 different types of energy bars. Alright, we're making a chocolate chip flavored, peanut butter brownie flavored, and we're going to set them to 2 different prices. Alright, X is the chocolate chip price in dollars. Y is the price of the peanut butter in dollars. Alright, and then we're going to sell them, and this is our profit equation. Alright, determine the selling point for both flavors that will optimize our profit, show our work, give correct unit. A lot of times this is how I'll word the question, so just so you know. Find the profit, verify using a test, show all your work, clearly label your derivatives, give your final solutions in the spaces provided. Alright, so first step. Alright, so step A is when we're showing all of our work, so find our critical values. Which means I find my first order derivatives and set them equal to 0. Alright, first order derivative in this case, looking at my x values, -1200x plus a +1200y minus 300 set equal to 0. And then with respect to y. Alright, -2400, sorry, -2400 y. 1200x plus 4500, set it equal to 0. Alright, so there's my first order derivative, and it's linear, and actually we've done this one before. Alright, but now we're doing it in terms of an application. Alright, it is a linear case, which means I can rewrite them and plug them in my matrix. So I'm going to rewrite them first. Alright, I add the constant to the other side, so I get -1200x. So I'll write it a little lower. That's the linear. Alright, so -1200x plus 1200y equals +300, and this one I add my 45. Sorry, subtract my 4500. So I'm going to get, and rewrite it, x first, so +1200, right? The x value first. Then the y value, the -2400y equals the -4500. Alright, so that's what we plug into our matrix. So again, just make sure you're careful, because there's 3 1200s, and just make sure you plug them in the right spots and with the right sign. Alright, so again, there is our matrix. And now we row reduce, right? Again, so you plug that into your matrix key on the calculator. Make sure you're careful. Watch out for your signs. It's really easy to miss a sign or misplace a number. Again, a common mistake is students to go here and we'll plug it into the matrix key and they'll write the 2400 in the wrong spot. Alright, so make sure you're careful. If you do plug it in correctly, you should row reduce and it should come out. So there's my x value, there's my y value, and so my critical point is 3.25 for the x value, 3.5 for the y value. Alright, and so those are my answers to part A. Alright, profit is optimized when the chocolate chip flavored energy bar is set at a price. So these are prices. So we set the chocolate chip flavor at a price of $3.25. The peanut butter bar is set at a price of $3, slightly higher price at $3.50. Well, to optimize profit, you've got to plug that into the profit equation. All right, so to find profit, all right, you take your critical value and plug it into the original one given in the profit. The original profit equation given in the function. So you're going to take that, and again, it should come out a dollar amount. So again, you're going to go back up here. And in this function, you're going to plug in the x value 3.25 and the y value 3.5. All right. So again, make sure you're careful because of decimals. Rule of thumb is a good idea. Just put parentheses around them, especially when you square them. And just be careful when you plug them in. So 325 goes in for x, 350 goes in for y. All right. When I did that, I got that my profit comes out to $10,125. All right, so there's my maximum profit. All right, so if we set the price of chocolate chip to $3.25, they'll sell so many. Peanut butter to $3.50, they'll sell so many. When they sell them, they'll earn a profit of $10,125. And now to make sure that that's true, right? I'm making those statements. Those are my optimum values. Well, now I should make sure and verify and prove that it is the case. So again, I have to set up my D test. So I need my second derivative with respect to x times my second derivative with respect to y minus my mixed derivative squared. So I'm going to go up above and find those because I need my first derivative. So again, I'm going to erase some stuff here to find. Give myself a little space to find my second derivatives. Alright, so the second derivative with respect to x, and then my mixed derivative, and then my second derivative with respect to y. They should come out numbers. Alright, so looking here first, finding its derivative with respect to x and then y. So with respect to x, it's negative 1200. With respect to y, it's a positive 1200. And then looking over here, its derivative with respect to y is negative 2400. Alright, so there are my values. I've got to go plug in my D formula. Negative 1200, negative 2400, and positive 1200. Alright, multiply those out. It comes out to a fairly large number. Alright, again, that just means, yep, it's an extrema. Alright, then I check my second derivative with respect to x, which was negative 1200. Yes, not only is it extrema, but it's turning the way I want it to, right? It's concave down. Well, if it's an extrema that's concave down, then yes, it's my maximum. Alright, and so that's what we mean by... So that's the explanation. Check that it is. The D-test checks that it's turning. The concavity checks that it's turning the way we want. And then we draw our conclusion. Yep, it's turning the way we want. And we get our optimum value. Alright, so the last one. Alright, so all of those were examples where I could either solve it straightforward, the first example. And the last two were the case where we had... we could plug it in and solve for a matrix. And so this last case, that we're going to look at is going to be a little more complex. I've got a cube, so I know I'm not going to be able to plug it into the matrix, and so we'll see what we get when we go to solve this. Alright, so we've got a company. They're offering space flights, trips to orbit the Earth. The company will charge two different prices depending on if you're a U.S. citizen or a foreigner. Alright, given by that equation in dollars per year, so this is the profit they estimate they'll get. Alright, so answer each question, show all work, determine the number of U.S. citizens, verify your answer. So again, basically just go through the same process we did before. Alright, find your critical value, test to see if the critical value gives your optimum value, and so on. Alright, so critical value first. Alright, so I'm going to find my first order derivatives here so I can look at my function. So I'm actually going to put them here, and then I'll write them in the next space. Alright, first derivative with respect to x, and then the first derivative with respect to y. Alright, so my x first. Alright, those are my x values. Everything else will zero out, so we get negative 3x squared, 480x, and 5100. Then my derivative with respect to y, well, those are the only two y values. Everything else will zero out, and so my y derivative is negative 4y, 176. Alright, I'm going to do my work down here. So it's only x values in this one, only y values in that one, and so I'll just solve the first equation for x. So set it equal to 0, and I'll solve that for x, and solve the second equation for my y. Alright, so there's my second derivative, or not second derivative, first derivative with respect to y, and then x. So it's just solve accordingly. Solve that one for x, solve this one for x, solve this one for y. I'm actually going to solve for y first because it's the easier one. Alright, I'm going to move my 176 to the other side. Negative 4y equals negative 176. Divide out by my negative 4. And so my y value is positive 44. Alright, now my x will take a little more work. Again, it's a quadratic, set equal to 0, so you can solve using the quadratic formula. Graph it, find its zeros, or factor. This one is factorable. First thing I'm going to do is I'm going to factor out a negative 3. I'm going to divide out a negative 3. When I do that, I have negative x squared, take 480, divide out by negative 3. It's going to be, negative 160, and then 5100 divided by negative 3 is negative 1700. Alright, this one does factor. Alright, x squared just splits up into x times x, and then I need factors of negative 1700. When I add, I get negative 160. Well, if I have negative 170, positive 10, right? If I take 10 and multiply it by negative 170, I get my negative 1700. If I take 10 and add it to 170, I get my negative 160. And so I have two answers, meaning this function has two critical points. Right? It's got one at an x value, positive 170, and one at an x value, negative 10. All right, but remember what the x values mean. The x value represents the number of people, right? Number of U.S. citizens who are going to take this flight. Well, I can't have negative U.S. citizens, right? And so I throw the negative out because it doesn't make any sense in context. Alright, so that means I really only have one critical value for this particular problem. My critical value is x value 170, y value 44. Alright, and so there's the answer to the first question. Alright, they plan to have 170 U.S. passengers, 44 foreign passengers. Alright, and that will optimize their profit. Alright, now in order to do the next step, I need to make sure that that answer is accurate. Alright, I need to do my d test. So remember the d formula is the second derivative of my function with respect to x times my second derivative with respect to y minus my mixed derivative squared. Mixed second derivative squared. Alright, so again, I'm going to go up here and find them and then plug them into my formula. Alright, so I've got to look here and here to find my second derivatives. Alright, again, I'm going to erase some space down here to write them out. Alright, so my second derivative with respect to x, my second derivative with respect to y, and then my mixed derivative. Alright, so looking here first, finding its derivative with respect to x again. Well, that's going to be a negative 6x plus 480. So I do have an equation this time. The mixed derivative is 0 because there aren't any mixed variables, right? So the mixed derivative zeroes out. Second derivative with respect to y, well, that's just negative 4. All right, so I have negative 4 times that function that I've got to plug into my d equation. So negative 6x plus 480 times a negative 4 and then 0 squared. All right, so when I go plug in my d formula, it was negative 6x squared plus 480 times a negative 4 minus 0 squared. And then I will simplify that because I am going to have to plug my value into it. And so it's just a little easier. I'm going to multiply through by my negative 4, so I get 2400x squared minus 1920. Alright, so there's the d-test. And now I'm going to test my point. So the value that I'm testing is my x value was 170, my y value was 44, and so I'm going to plug that in. So it's 24 times 170 squared minus 1920. Comes out to a really big positive number, which is good because we wanted it to be a big positive number, right? D comes out positive. That checks that yes, it's an extrema. Right, that's all it tells me. All right, it tells me that, yeah, it's either a max or a min. It's not a saddle point. So, yes, it's an extrema. All right, now I need to make sure it's the one I want. All right, now technically you could do XX or YY. All right. If you do XX, you do have to plug your point in because remember that was the derivative with respect to x. And so negative 6x squared plus 480. We'll plug in your x value, which was 170 squared plus 1480. All right, that comes out a negative number. Which I don't have written down anywhere, but it does come out negative. All right, it comes out negative, which means that's concave down, which is what we want, right? We want concave down in order for it to be a maximum. The other thing you could do, you could check the YY. The YY is actually easier. It already came out negative 4, right? Remember, the d-test means my x direction and my y direction are turning the same way. And so the concavity should be the same. So in the x direction, if it's concave down, in the y direction, it should be concave down. That's what the d-test is telling me. And so you could actually check either of them. The y direction's a little easier to check. We just, again, write a standard way to do it just to make life easier, but technically I could check either one. They should check the same way. All right, so it checks. All right, concave down. Yes, it's turning the same way, so we do have an extrema. And the last thing is to find it. And so take our profit equation, plug in 170 for x, 44 for y, and if you do that back in the original profit equation, it comes out a fairly large number, almost 2 million. Alright, and that's how much profit they should make. Which means they're probably selling these tickets at a very, very high price. Alright, we will stop there. So that finishes up 6.3. We skip 6.4. There's one last section left in Chapter 6, which are still optimization cases, but it's now looking... Remember, there are two ways to do optimize, right? Open case and closed case. This is the open case, right? Second derivative test is used when we're doing things with the open example. The next example is going to be like the closed case. So 6.5 is where we're going, and what it is going to resemble is we're going to optimize when we're limited. All right, we can't look at all x and y values, but we're limited to the x and y values that we can look at. All right, and so that's the next set of notes.